Recently, 4 astronauts flew around the moon and came home. The world celebrated, the flags went up, the speeches poured in, and almost immediately, the conversation turned to what comes next. Landing, building, staying. But here is what almost nobody is talking about. The moon is not what you think it is. It is not the gentle silver landmark hanging in your sky. It is a world where the ground beneath your feet is coated in glass shards finer than talcum powder that destroy lungs from the inside. Where daytime temperatures reach 260 degrees Fahrenheit and nightfall drops to -280. Where radiation pours through your body every second with nothing, not a single molecule of atmosphere, standing in the way. The harsh truth is not that we should never go back. It is that most people have no idea what going back actually means. If this is the kind of science storytelling that pulls you in, hit like and subscribe. We dig into the stories, the headlines skip over, and we do it properly. Now, are you comfortable? Let's begin. On April 1st, 2026, a rocket lifted off from Kennedy Space Center in Florida, carrying 4 human beings toward the moon. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen sat inside a spacecraft called Integrity and rode a column of fire into the black. 9 days later, they splashed down in the Pacific Ocean off the coast of California. The mission was called Artemis II. It was the first time human beings had traveled to the moon since December of 1972. More than 53 years of silence, and then a roar. The world watched. News cameras followed the rocket from the launch pad to the sky. Social media flooded with images of Earthrise taken through Orion's windows, photographs so vivid you could see city lights on the night side of the planet. The glow of Europe and Africa caught in the lens of someone falling around the far side of the moon at thousands of miles per hour. For 40 minutes during the lunar flyby, the crew lost all contact with Earth. The moon blocked every signal. 4 people drifted behind 250,000 miles of rock in total radio silence, farther from home than any human being had ever been. They set a new distance record during that pass, 252,756 miles from the surface of the Earth. And when they came back, the celebrations began. The speeches praised the beginning of a new era. The headlines declared that humanity had returned to the moon. Social media erupted with countdowns to the next step. Artemis III is planned for 2027, a mission to test docking with lunar landers in Earth orbit. Artemis IV, targeted for 2028, is expected to carry astronauts to the surface. After that, the plan calls for roughly 1 landing per year, a permanent base, a sustained human presence, eventually a stepping stone to Mars. And here is what almost no one paused to ask during any of it. What are we actually walking into? Not the moon of memory, not the moon of grainy footage and triumphant speeches, not the moon of flags and footprints and the ghostly bounce of astronauts hopping across a grey plain in slow motion. That moon exists only in history and in the imagination. The real moon, the physical object hanging 240,000 miles above your head right now, is something else entirely. And the distance between what people think the moon is and what the moon actually is may be the single most dangerous gap in the entire future of human space exploration. To understand why that gap exists, you need to understand something about the way human beings process familiarity. There is a cognitive pattern that researchers have documented across dozens of fields, from aviation safety to financial risk analysis. When people encounter something repeatedly without being harmed by it, they stop perceiving it as dangerous. The signal fades, the alarm gets quieter. Not because the danger decreased, but because the brain decided it was no longer worth flagging. Pilots call it normalization of deviance, Safety engineers call it risk habituation. And when it comes to the moon, the entire human species has been doing it for decades. Think about what the moon is in most people's lives. It is the first astronomical object a child learns to point at. It is the thing outside the window on a clear night. It is a symbol in poetry, a setting in stories, a backdrop in films. It is so present, so constant, so visually familiar that it barely registers as a foreign world at all. You have seen it thousands of times. You know the shape of its craters. You know the way it looks, full, half, crescent. You know where it sits relative to the stars. You might even know its name in 3 or 4 languages. And all of that knowing, all of that comfortable recognition does something very specific inside the brain. It files the moon under safe, under understood, under close enough to be manageable. Now compare that to how people think about Mars. Mars is alien, Mars is red, Mars is far. Everyone intuitively grasps that Mars is hostile because it looks hostile. It sits so deep in the solar system that a one-way signal takes up to 24 minutes. The distance alone triggers a psychological warning. Nobody looks at Mars and thinks, "We have been there before, it will be fine." Mars earns its respect from sheer unfamiliarity. The moon earns none of that caution. The moon earns the opposite, because we went there, because we walked on it. Because 12 human beings touched its surface and came home alive and smiling. The Apollo program did something miraculous for science and something quietly catastrophic for public risk perception. It made the moon feel like a place we had already handled. But here is what the Apollo missions actually were. They were sprints. The total time human beings have spent on the surface of the moon across all 6 landing missions is approximately 300 hours. 300 hours. Not 300 days. Not 300 weeks. 300 hours spread across 6 visits over 3.5 years, with barely 80 of those hours spent outside the lander on actual moonwalks. The longest single-surface stay was Apollo 17, which kept astronauts Eugene Cernan and Harrison Schmitt on the ground for about 75 hours, 3 days. And during those 3 days, the astronauts were essentially camping. They had a lander that served as their shelter, a rover that ran on batteries, and suits that provided a few hours of life support per excursion. Everything they needed came with them from Earth. Everything they left behind was expendable. The entire operation was designed around one principle: get in, do the work, get out before the environment kills you. Nobody stayed long enough to experience a full lunar night. Nobody dealt with the cumulative effects of radiation exposure over weeks or months. Nobody had to repair a critical system using only what was available on the surface. Nobody had to grow food, recycle water, or manage the slow psychological erosion of living in a place that is actively trying to destroy every piece of equipment you depend on. Apollo was a proof of concept. It proved that human beings could survive on the moon for a few days. It did not prove, and was never designed to prove, that human beings could live there. The distinction matters more than almost anyone realizes, because the missions being planned right now are not Apollo. They are not sprints. The architecture being developed for Artemis and the programs that follow it envisions astronauts spending a week or more on the surface per mission, eventually building towards stays of weeks and months at a time. The goal is not to visit the moon. The goal is to inhabit it. And inhabiting the moon is a fundamentally different engineering, medical, and psychological problem than visiting it. Here is an analogy that captures the scale of the difference. Imagine you once spent a weekend camping at the edge of a desert. You packed your food, brought your water, slept in a tent, and drove home on Sunday. Now, imagine someone told you that because that weekend went well, you should move to the center of that desert permanently build a house out of whatever you find on the ground, and figure out how to survive indefinitely with supply deliveries that come once or twice a year and take 3 days to arrive in an emergency. The weekend trip did not prepare you for that. It did not even give you the information you would need to understand how unprepared you are. The moon is that desert, and the Apollo missions were the weekend camping trip. The experience was real. The achievement was extraordinary. But the lessons it taught about long-term survival on the lunar surface are almost none. To understand just how different inhabiting is from visiting, think about what a single ordinary day would look like for an astronaut living on the lunar surface during an extended mission. They wake inside a habitat that has been running on stored power for days because the sun has not risen yet. The first task is not science, it is maintenance. Every morning begins with a systems check. Life support status, oxygen generation rates, carbon dioxide scrubber performance, water recycling efficiency, power reserves and draw rates, thermal control system status, communication link verification. These are not optional tasks that can be postponed if the crew is tired or busy. They are the things that keep the air breathable and the walls warm. If any of them are trending in the wrong direction, the rest of the day's plan changes. If a surface excursion is scheduled, the preparation alone takes hours. The spacesuits used for lunar EVA are not garments you pull on like a jacket. They are self-contained spacecraft in miniature. Donning a suit involves a pressurization sequence, a leak check, a communication check, a thermal system activation, a life support system priming, and a final review of consumables, oxygen supply, battery charge, cooling water. The process must be performed correctly every time. A mistake during suit-up is not an inconvenience. It is a potential fatality waiting to express itself 3 hours later when the astronaut is a kilometer from the airlock. Once outside, the astronaut is on a clock. The suit carries a finite supply of everything the body needs: oxygen, power, cooling water, and carbon dioxide absorption capacity all count down from the moment the outer hatch opens. EVA durations are planned around whichever consumable runs out first, and the schedule must include a margin for contingencies because the walk back to the airlock is not a sprint, it is a careful, deliberate traverse across terrain that can hide ankle-turning depressions under a layer of dust that all looks the same in the flat lunar light. When the astronaut returns and repressurizes the airlock, the next challenge begins immediately. The suit is covered in dust. Every surface that was exposed to the regolith must be cleaned or isolated before the inner hatch opens, because once that dust enters the habitat's air supply, it does not leave easily. The cleaning protocols add time and complexity to every single EVA cycle. Over weeks and months, the protocol itself becomes a source of fatigue, a repetitive chore performed at the end of an exhausting physical excursion in a suit that weighs roughly the equivalent of 100 pounds in Earth terms, even at 1/6 gravity. The evening is not rest in any meaningful sense. It is the second half of the maintenance cycle: suit inspection, consumable inventory, data uploads, equipment recharging, science sample cataloging, meal preparation from pre-packaged or rehydrated food in a space that is smaller than most people's bathrooms, and then sleep in a compartment that hums with the continuous sound of fans and pumps that must never stop. This is not the experience depicted in concept art. There are no panoramic windows. There are no spacious common areas. There is no moment where an astronaut leans back and gazes at Earth in peaceful contemplation. The real daily rhythm of lunar habitation is dominated by systems management, protocol execution, and the constant low-level awareness that the margin between comfort and crisis is thinner than it has ever been for any human being in any environment on Earth. The Apollo astronauts never experienced this. They were on the surface for hours, not weeks. Their daily rhythm was defined by a mission timeline measured in minutes, not by the grinding repetition of survival protocols that must be performed identically on day 1 and day 60 and day 120. The endurance required is not physical in the way climbing a mountain is physical. It is operational. It is the sustained, relentless, error-free execution of procedures that keep you alive in a place where the environment offers no second attempt. And yet the public conversation has skipped past all of this. The framing in the media, in government statements, in popular science communication is that we are going back to the moon. The word back does something subtle and powerful. It implies return. It implies familiarity. It implies that the destination is known, that the route has been traveled, that the risks have been mapped. We are not going to the moon for the first time. We are going back. The language itself carries a built-in reassurance that is almost entirely false. Because the moon we are going back to is not the moon of 1969 or 1972. It is the same physical object, but everything about the mission profile has changed. The duration has changed. The objectives have changed. The expectations for what astronauts will do on the surface have changed, and the technology, while vastly more capable in some ways, is also being asked to do things that no technology has ever been tested against in this environment for these durations. Let us be specific about what has changed since Apollo. The planned Artemis landing missions will target the lunar South Pole. This is not where Apollo went. All 6 Apollo landings occurred at relatively low latitudes near the lunar equator in regions that were well lit and well mapped. The South Pole is a different world. It is a landscape of permanently shadowed craters where temperatures drop to minus 238 degrees Celsius, colder than the surface of Pluto. Adjacent to those craters are ridges and peaks that receive sunlight more than 80% of the time, creating temperature gradients so extreme that stepping from shadow into light means crossing a boundary of hundreds of degrees within a few feet. The terrain is rugged, poorly mapped compared to the equatorial sites, and littered with hazards that orbital imaging can identify but cannot fully characterize. No human being has ever set foot in a place like this. The South Pole was chosen for a reason. Scientists believe that the permanently shadowed craters there contain deposits of water ice trapped for billions of years in the cold. That water is potentially the most valuable resource on the moon. It could be split into hydrogen and oxygen, providing breathable air and rocket propellant. It could support a sustainable human presence without the need to ship every molecule of water from Earth. Finding and characterizing that ice is one of the central scientific goals of the Artemis surface missions. But the very conditions that preserve the ice are the conditions that make the region so punishing for human operations. The permanently shadowed regions are not just cold, they are among the coldest measured environments in the entire solar system. Equipment designed to function in those conditions must survive temperatures that challenge the physical limits of most known materials. Metals become brittle, lubricants freeze, batteries lose capacity, seals contract and fail. Every component that enters a permanently shadowed region is operating at the bleeding edge of its design tolerance, and the astronauts exploring those regions will be operating at the edge of theirs. The suits being developed for surface operations, the Axiom Extravehicular Mobility Unit, represent a massive leap forward from Apollo-era technology. They offer greater mobility, better thermal management, and longer operational duration. But no suit is a self-contained habitat. A suit is a temporary bubble of survivability wrapped around a human body. It has a limited air supply, limited power, limited ability to reject heat or retain it depending on conditions. Every minute an astronaut spends in a suit on the lunar surface is a minute on a countdown. And the clock does not stop when something goes wrong. Consider what going wrong looks like on the moon. On Earth, if a critical piece of equipment fails during a field operation, you call for help. A helicopter arrives. A truck brings replacement parts. A hospital is hours away at most. On the International Space Station, if a medical emergency occurs, a Soyuz capsule can undock and return to Earth in a matter of hours. The station orbits at roughly 400 kilometers above the surface. It is close. The moon is not close. It is approximately 384,000 kilometers from Earth. A journey from the surface to low Earth orbit takes roughly 3 days. But that 3-day number assumes a spacecraft is fueled, ready, and positioned for departure. It assumes the launch window is correct. It assumes no systems have been compromised by the same emergency that created the need to leave. In a real crisis, the time between the moment something goes wrong on the lunar surface and the moment an astronaut could reach an Earth hospital is not 3 days. It is significantly longer. It might be a week. It might be more. And for certain types of emergencies, it might be never. There is no search and rescue on the moon. There is no Coast Guard. There is no ambulance. There is no backup crew on standby, ready to launch at a moment's notice. If an astronaut is injured during a surface excursion at the South Pole, the other crew members will have to provide whatever care they can with whatever they brought. The nearest surgeon is 250,000 miles away, and there is no way to shorten that distance. This is the reality that the word back obscures. We are not returning to a place we understand. We are going to a place we touched briefly, under controlled conditions, with escape routes planned in advance, and we are now proposing to stay. The difference between those two things is the difference between holding your hand over a candle flame for 1 second and holding it there for a minute. The first is a stunt. The second is a burn, and the public does not feel this. The public sees the moon through the window and thinks, it is right there. 240,000 miles sounds like a lot until you remember that the Apollo astronauts crossed it in 3 days. 3 days. That is a long weekend. That is a drive from New York to Los Angeles with a stop for gas. The number is small enough to feel manageable, and the human brain locks onto that feeling and discards the rest. This is not a criticism of public enthusiasm. The excitement around Artemis is genuine and in many ways justified. The engineering achievements are real. The science is important. The vision of humanity, extending its reach beyond Earth, is one of the most compelling ideas our species has ever pursued. But enthusiasm and understanding are not the same thing. And right now, the gap between the two is wide enough to be dangerous. Because when people hear that astronauts are going to live on the moon, they picture something. They picture a base, a habitat with windows, a place where astronauts eat meals and run experiments and look out at the grey horizon. The image in their heads is derived from decades of science fiction, from films and television shows and concept art released by space agencies. It is clean, bright, controlled. It looks like a research station in Antarctica or a submarine under the ocean. Challenging, yes. Isolated, certainly. But manageable, survivable. Even comfortable in a rugged sort of way. That image is a fantasy. Not because the engineering is impossible, but because it leaves out everything that makes the moon the moon. It leaves out the radiation pouring through the walls. It leaves out the dust eating into every seal and hinge. It leaves out the 14-day darkness that turns thermal management into a crisis. It leaves out the psychological weight of knowing that if the habitat fails, there is nowhere to go. The concept art does not show the astronaut lying awake at 3 a.m, wondering whether the oxygen recycler will make it through the next lunar night. It does not show the slow accumulation of damage to equipment that was never designed to be maintained with the limited tools available on the surface. It does not show the moment when a mission controller on Earth realizes that a problem has developed that cannot be fixed remotely and cannot wait 3 days for a solution. The moon does not care about our plans. It does not care about our timelines. It does not care that we were there before. It is 250,000 miles of vacuum, radiation, temperature extremes, and abrasive dust, and it has been sitting there for 4.5 billion years, waiting for nothing and expecting nothing. Every gram of air, every watt of power, every calorie of food, every drop of water that a human being needs to survive on its surface must be brought from Earth or extracted from a landscape that does not want to give it up. That is the foundation on which every lunar return mission is built. Not on the romance of exploration, not on the legacy of Apollo, not on the beautiful images of Earthrise taken through the windows of a spacecraft that has already come home. It is built on the raw physics of survival in a place that offers nothing except the opportunity to die if you make a mistake, and most people do not know this. Most people have never been told this in plain language, because the language around lunar exploration has been optimized for excitement rather than accuracy. The press releases emphasize milestones and achievements. The speeches talk about destiny and discovery. The concept videos show astronauts bounding across the surface in pristine suits, with Earth hanging perfectly in the background. None of it is a lie. But none of it is the whole truth either. The whole truth starts with what happens to the human body the moment it leaves the protection of Earth's magnetic field and atmosphere. Because the moon does not just lack comfort, it lacks the single most important shield that every living thing on this planet depends on without ever thinking about it. And what that shield has been doing for you every second of your life is something most people have never been asked to consider. The story of that shield and what happens when it disappears is where the real reckoning begins. Right now, as you listen to this, something is trying to kill you from space. Charged particles launched from the surface of the sun, protons and electrons riding shockwaves from stellar explosions, and heavy atomic nuclei, stripped of their electrons and accelerated to nearly the speed of light by forces in distant corners of the galaxy, are all streaming toward you at this very moment. They have been doing it since the day you were born. They will keep doing it until the day you die. And you have never once felt a single one of them. The reason you have never felt them is that you live inside a machine so large and so ancient that no human being thinks of it as a machine at all. Earth itself is a radiation shield. It runs 2 systems simultaneously, and together they form the most sophisticated particle deflection apparatus in the inner solar system. The first system is the magnetosphere. Deep inside the planet, a churning ocean of liquid iron generates a magnetic field that extends tens of thousands of miles into space, forming an invisible bubble around the Earth. When charged particles from the Sun or from beyond the solar system encounter this bubble, most of them are deflected. They spiral along the magnetic field lines toward the poles, where some of them collide with atmospheric molecules and produce the aurora. The rest are flung back into space. They never reach the surface. The second system is the atmosphere itself. Earth's blanket of gas is roughly 60 miles thick, and its combined mass is equivalent to a layer of water about 10 meters deep covering the entire planet. Any particle that makes it past the magnetosphere still has to punch through that mass of air before it can reach you. Most of them do not. The atmosphere absorbs, scatters, and fragments incoming radiation so effectively that the total annual dose a person receives from cosmic sources at sea level is approximately 0.4 millisieverts. That is a vanishingly small number. It is roughly 1/6 of the total background radiation dose you absorb each year from all natural sources combined. You have lived your entire life inside those 2 overlapping shields. Every cell in your body developed under their protection. Every organism that has ever existed on this planet evolved in an environment where high-energy cosmic radiation was filtered down to a biologically manageable trickle. The shielding is so effective and so constant that for most of human history, people did not know it existed. It took centuries of physics to even understand what it was blocking. The Moon has neither of these systems. It has no global magnetic field. The remnants of an ancient field survive as faint patches of crustal magnetism in a few scattered locations, but these are hundreds of times weaker than Earth's field and cover only tiny fractions of the surface. They provide no meaningful protection against energetic particles. The Moon also has no atmosphere. The word "no" is doing real work in that sentence. Earth's atmosphere contains roughly 5 quadrillion metric tons of gas. The Moon's exosphere, the technical term for the almost imperceptible haze of molecules hovering near its surface, contains so few particles that a single cubic centimeter of air at Earth's sea level holds 100 trillion times more molecules than the same volume of space at the lunar surface. For all practical purposes, the Moon is naked. Its surface is directly exposed to the full radiation environment of interplanetary space, unfiltered, unshielded, and relentless. This means that from the instant an astronaut steps onto the lunar surface, their body is being struck by every particle the cosmos sends, not a filtered trickle. The full stream. And that stream has 2 main components, each dangerous in its own way. The first is galactic cosmic radiation. These are particles that originate outside the solar system, primarily protons and helium nuclei, but also heavier ions from elements all the way up the periodic table. They have been accelerated by supernova shockwaves, by the magnetic fields of pulsars, by violent events in other galaxies. By the time they reach the inner solar system, some of them are traveling at more than 99% of the speed of light. They carry enormous energy, and their defining characteristic from a biological perspective is that they are almost impossible to stop. When a galactic cosmic ray enters a human body, it passes through tissue like a bullet through fog. It does not stop at the skin. It does not stop at the muscle. It punches through organs, through bone, through the delicate structures of the brain. Along its path, it ionizes atoms, breaking molecular bonds, shattering DNA strands, and leaving a trail of cellular damage that the body's repair mechanisms must scramble to fix. A single heavy ion can damage every cell it passes through, and these particles arrive constantly. There is no moment on the lunar surface when they are not hitting you. There is no time of day, no season, no orientation of the sky that offers a reprieve. The second component is solar energetic particles. These are protons and electrons ejected from the sun during solar flares and coronal mass ejections. Unlike galactic cosmic rays, which arrive at a relatively steady rate modulated by the solar cycle, solar particle events are sporadic and unpredictable. They can erupt with little warning. A massive solar flare can accelerate billions of tons of charged material to speeds of several million miles per hour, sending a wave of radiation outward through the solar system that reaches the Moon in as little as 15 minutes to a few hours, depending on the energy and trajectory of the event. On Earth, you would never know it happened. The magnetosphere catches the wave. The atmosphere absorbs what leaks through. A particularly strong event might cause a geomagnetic storm that disrupts satellite communications or triggers unusually vivid auroras. But you, standing on the surface, are fine. Your body never registers the event. On the Moon, you would be standing in the open. The full flux of a solar particle event would hit the surface, with nothing between it and your cells except whatever material your spacesuit or habitat is made of. And for the largest events in the historical record, that material may not be enough. Here is where the numbers become difficult to take in without pausing. In 2020, China's Chang'e 4 lander, which touched down on the far side of the Moon in January 2019, published the first direct measurements of radiation dose rates on the lunar surface. The lunar lander, neutrons, and dosimetry experiment recorded an average total absorbed dose rate of approximately 13.2 microgray per hour. When converted to biologically relevant units and adjusted for the types of radiation involved, the effective dose rate for an astronaut on the surface comes to roughly 1,369 microsieverts per day. That is approximately 2.6 times the daily dose received by crew members aboard the International Space Station. That comparison requires immediate context, because the International Space Station is not a safe environment by Earth standards. Astronauts on the station receive radiation doses roughly 10 times higher than people on the ground. They develop elevated risks of cancer, cataracts, and cardiovascular disease. NASA tracks their cumulative exposure carefully and limits career duration partly based on radiation thresholds. The ISS is already a high radiation workplace, but the station has an advantage that the Moon does not. It orbits within Earth's magnetosphere. At an altitude of roughly 400 kilometers, the ISS sits inside the protective bubble. The magnetic field deflects a significant portion of incoming galactic cosmic rays and almost all solar energetic particles under normal conditions. The station's radiation environment, while elevated, is still filtered. The Moon sits entirely outside that bubble. The dose rates measured by Chang'e 4 represent the unfiltered radiation environment of interplanetary space, hitting the surface from above and, critically, also reflecting upward from the ground. When galactic cosmic rays and solar particles strike the lunar regolith, they generate a secondary spray of neutrons and gamma rays that radiates back up from the soil. An astronaut on the Moon is irradiated from both directions simultaneously, from the sky and from the ground they are standing on. The annual effective dose from galactic cosmic radiation alone on the lunar surface is estimated at roughly 380 millisieverts during solar minimum, the period when the Sun's magnetic activity is weakest and galactic cosmic rays penetrate most freely into the inner solar system. During solar maximum, the Sun's stronger magnetic field partially deflects incoming galactic particles, reducing the dose to roughly 110 millisieverts per year. For comparison, the average annual radiation dose for a person on Earth from all natural sources is approximately 2.4 millisieverts. At solar minimum, an astronaut on the Moon receives in a single year more than 150 times the dose that a person on Earth receives. And this is the baseline. This is what the Moon delivers on a quiet day. The quiet days are not the problem. The problem is the days that are not quiet. Solar particle events are the acute threat. They arrive without reliable long-term warning. Space weather forecasting has improved significantly in recent decades, but the ability to predict exactly when a major solar eruption will occur, how energetic it will be, and whether the resulting particle stream will be directed toward the Moon remains limited. Current systems can typically provide warnings, ranging from minutes to a few hours, once an event has already begun. For an astronaut inside a habitat, that warning time may be sufficient to move to a more shielded area. For an astronaut on a surface excursion several kilometers from base, several hours into an EVA, it may not be. The scale of what a large solar particle event can deliver is sobering. Researchers have studied the historical record of solar events, going back decades using measurements from orbiting instruments and proxy data from ice cores and tree rings going back centuries. The events vary enormously. Small events may deliver doses that are biologically trivial. Moderate events might deliver tens of millisieverts over a few hours. But the largest events on record, and the ones that statistical models suggest will occur periodically over the decades of a sustained lunar program, can deliver effective doses of several hundred millisieverts to an unshielded person in a matter of hours. Several hundred millisieverts in hours. To put that in perspective, the threshold for acute radiation syndrome, the clinical condition commonly called radiation sickness, begins at approximately 700 millisieverts delivered over a short period. Symptoms include nausea, vomiting, fatigue, and immune system suppression. At higher doses, the damage escalates to hemorrhaging, organ failure, and death. The very largest solar particle events in the historical record, such as the Carrington event of 1859 or the event of August 1972, which occurred between the Apollo 16 and Apollo 17 missions, could potentially deliver doses in the range of several thousand millisieverts to an unshielded human on the lunar surface. That is not a survivable exposure. The August 1972 event is particularly haunting for the history of human spaceflight. It erupted during a gap between two Apollo missions. If it had occurred a few months earlier or a few months later, astronauts would have been on the lunar surface or in transit between Earth and the Moon. The spacecraft and suits of that era provided minimal radiation shielding. Whether the crew would have survived is a question that has been debated in the radiation biology community for decades. The most honest answer is that they would have been in serious danger. Some analyses suggest the exposure could have been career-ending. Others suggest it could have been fatal. The fact that no Apollo crew happened to be in space during that event is one of the quieter pieces of luck in the history of exploration, and this is the part that rarely enters the public conversation. The Apollo astronauts were not protected from solar particle events. They were lucky. The missions were short enough, and the solar activity during those windows was mild enough that no crew encountered a major event. But luck is not a radiation shield. And a sustained program that puts astronauts on the lunar surface repeatedly over years and decades cannot rely on luck. The probability of a major solar particle event occurring during any given week is low. The probability of one occurring during a 10-year program of annual surface missions is not low at all. It approaches certainty. NASA and other agencies are aware of this. The current plans for lunar surface operations include requirements for radiation shelters, areas within habitats or vehicles that provide additional shielding, where astronauts can retreat during a solar storm warning. The Artemis suit designs incorporate radiation monitoring. Operational protocols call for EVAs to be planned around solar activity forecasts and for emergency ingress procedures if a warning is issued during a surface excursion. These measures are real, and they represent genuine engineering progress. But they also carry assumptions that deserve scrutiny. They assume that warnings will arrive in time. They assume that the astronaut will be close enough to shelter to reach it before the particle flux becomes dangerous. They assume that the shelter itself will provide sufficient shielding, which depends on its mass, its material composition, and the energy spectrum of the specific event, all of which vary, and none of which can be known perfectly in advance. And they assume that equipment will function correctly during the event, that hatches will seal, that life support will not be compromised, that the power system will hold up under conditions it may not have been tested against at full scale. Every one of those assumptions is reasonable, none of them is guaranteed. And on the Moon, the distance between a reasonable assumption and a guaranteed outcome is measured in lives. There is a deeper biological dimension to this that extends beyond acute events. The chronic exposure to galactic cosmic radiation, the background dose that accumulates day after day regardless of solar activity, produces effects that are slower to appear but no less serious. Research over the past 2 decades has identified several categories of long-term damage associated with the types of radiation found in deep space. cancer risk is the most widely discussed. The heavy ions in galactic cosmic rays are particularly effective at damaging DNA in ways that the body's repair mechanisms struggle to correct. Unlike the low-energy radiation encountered in medical imaging or even in terrestrial occupational settings, heavy ions produce clustered damage along their tracks, breaking multiple strands of DNA simultaneously in ways that are more likely to produce mutations than clean single-strand breaks. The resulting mutations can lie dormant for years before producing detectable tumors. NASA's current models estimate that a 6-month mission on the lunar surface during solar minimum would increase an astronaut's lifetime cancer risk by a measurable percentage. For longer stays, the risk compounds. Central nervous system effects are less well understood but potentially more alarming. Animal studies conducted at particle accelerator facilities, where researchers can simulate the types of radiation found in deep space, have shown that exposure to heavy ions can produce cognitive deficits, memory impairment, and behavioral changes in rodents at doses comparable to what astronauts would accumulate during extended lunar missions. The mechanisms appear to involve damage to the synaptic connections between neurons, the structures that underlie learning, memory, and decision-making. Whether these effects translate directly to humans is still an open question, but the animal data has been consistent enough to make it a priority research concern for every space agency planning long-duration missions beyond low Earth orbit. Cardiovascular disease is another emerging concern. A study, published in 2016, examined the health records of Apollo astronauts who traveled beyond low Earth orbit and found that their rates of cardiovascular mortality were significantly higher than those of astronauts who flew only in low Earth orbit, or who never flew at all. The sample size was small, and the study's authors were careful to note its limitations. But the finding was consistent with laboratory research, showing that space radiation can damage the endothelial cells lining blood vessels, promoting the development of atherosclerosis. If confirmed by larger studies, this would mean that the radiation environment of the Moon does not just increase cancer risk. It increases the risk of heart attacks and strokes, potentially for years after the exposure ends. And then there is a compounding effect that researchers have only recently begun to investigate seriously. Radiation damage does not occur in isolation on the Moon. It occurs simultaneously with exposure to lunar dust. Recent laboratory research has shown that lunar dust becomes more biologically aggressive after prolonged exposure to the space environment, a process we will examine closely shortly. What matters here is the implication for radiation biology. An astronaut who inhales chemically activated lunar dust while simultaneously receiving elevated radiation doses may experience synergistic effects where the combination is worse than the sum of its parts. Radiation weakens lung tissue at the cellular level. Activated dust particles attack that weakened tissue through a separate chemical pathway. The immune system, already suppressed by the space environment, struggles to mount an effective response to either insult. The interaction has not been fully characterized, because it is extraordinarily difficult to replicate under controlled laboratory conditions. But the theoretical basis for concern is strong enough that multiple research groups have flagged it as a priority for pre-mission investigation. This is what the radiation environment of the Moon actually looks like when you strip away the abstractions and the reassuring language of mission planning documents. It is a continuous, invisible, whole-body assault that begins the moment you leave Earth's magnetic field and does not stop until you return to it. It cannot be felt. It cannot be seen. It produces no immediate sensation. An astronaut standing on the lunar surface during a quiet period of solar activity would feel perfectly fine. They would see nothing unusual. Their instruments would show them the dose rate climbing, silently, steadily, cell by cell. The insidiousness of radiation is that it is a threat that does not announce itself. Fire is hot. Vacuum is breathless. Cold is painful. Radiation is silent. And by the time its effects become clinically apparent, the damage has often been accumulating for months or years. An astronaut who completes a 6-month lunar surface mission and returns to Earth feeling healthy may begin to develop symptoms years later. The cataracts that form, the tumor that appears, the cognitive decline that sets in earlier than expected. These are not failures of the mission. They are the mission's delayed cost, paid in the currency of the astronaut's body, and the cost is not optional. There is no technology currently in existence or in development that can fully shield a human being from galactic cosmic radiation on the lunar surface. The particles are too energetic. Stopping them requires either extremely thick layers of mass, on the order of several meters of regolith or equivalent material, or active magnetic shielding systems that remain in the early conceptual stage and are nowhere near deployment readiness. The habitats planned for initial Artemis surface missions will provide some shielding, enough to reduce doses during normal operations and to offer meaningful protection during moderate solar events. But they will not eliminate the background galactic dose. They cannot. The physics does not allow it with any structure that can be practically transported to or assembled on the Moon with near-term technology. What this means in plain terms is that every astronaut who lives on the lunar surface for an extended period will accumulate radiation damage. The goal of mission planning is not to prevent exposure, but to manage it, to keep the cumulative dose within limits that space agencies have defined as acceptable risk. Those limits exist. They are based on models of cancer risk and are periodically revised as new data becomes available. But acceptable risk is a policy decision, not a physical barrier. It means that the agencies have decided the science and the strategic value justify a certain probability of long-term health consequences for the people they send. The astronauts will be informed. They will consent. They will go, and their bodies will record every particle that passes through them, whether they feel it or not. This is the invisible war the Moon wages against every human being who sets foot on its surface. Not with drama, not with explosions, not with the kinds of dangers that make for exciting film sequences, with particles too small to see, arriving too fast to track, doing damage too subtle to feel. The Moon does not need to be violent. It simply needs to be unshielded. And it is the most unshielded place any human being has ever been asked to live. But radiation is only the assault you cannot see. There are others, just as relentless, that attack through channels far more tangible. The ground you walk on, the temperature that swings across 300 degrees, the engineering margins that shrink with every passing hour. What comes next is about the enemies you can touch, and the ones that touch you back. In December of 1972, astronaut Harrison Schmitt climbed back into the Apollo 17 lunar module after his first moonwalk in the valley of Taurus Littrow. He and Commander Eugene Cernan had spent hours working on the surface, collecting rock samples, deploying instruments, driving the lunar rover across a landscape no human being had ever touched. The work was physically demanding but successful. The science was extraordinary. And then Schmitt took off his helmet. Within seconds, his nose began to swell. His eyes reddened, his throat itched. His sinuses clogged. He started sneezing and could not stop. The symptoms were so pronounced that you could hear the congestion in his voice on the radio transmission back to Earth. Mission Control noticed. Someone in Houston cracked a joke about cheap noses. Everyone laughed. But what was happening inside that lunar module was not a joke. It was the first documented allergic response to an extraterrestrial material in the history of human exploration, and it was caused by something so fine, so pervasive, and so adhesive that no amount of brushing, vacuuming, or protocol could keep it out. Lunar dust. Schmidt's reaction was the most dramatic, but he was not alone. Every Apollo crew that landed on the moon reported problems with dust. The Apollo 11 astronauts noted that it covered everything and left stains that resisted all attempts to remove them. An Apollo 12 crew member said the module had so much dust inside that when he removed his helmet, he was nearly blinded. Across all 6 landing missions, the pattern was the same. The dust got into everything. It coated visors, clogged mechanisms, abraded suit fabrics, and filled the cabin air the moment the hatch was sealed. The astronauts could smell it. They described the odor as burnt gunpowder, a sharp metallic scent that hung in the enclosed space and clung to every surface. The smell itself is a clue to something far more dangerous than simple dirt. Lunar dust is not like any dust on Earth. It has never been weathered. On our planet, wind and water tumble particles against each other for millions of years, grinding off sharp edges, rounding them into relatively smooth grains. The dust you wipe from a shelf, the sand on a beach, the silt in a riverbed, all of it has been softened by erosion. Lunar dust has experienced none of that. The moon has no wind. It has no water. It has no process that rounds or smooths anything. Instead, the primary mechanism that creates lunar dust is impact. Micrometeorites, tiny fragments of rock and metal traveling at tens of thousands of miles per hour, slam into the surface continuously. Each impact fractures the regolith into smaller and smaller particles. The result is a powder composed of grains with edges as sharp as freshly broken glass, jagged on a microscopic scale in a way that terrestrial dust almost never is. These particles are extraordinarily small. Many are less than 20 microns across. For reference, a human hair is roughly 70 microns wide. Particles below about 10 microns can penetrate deep into the lungs, reaching the alveoli, the tiny air sacs where oxygen enters the bloodstream. Particles at the scale of lunar dust do not just irritate the upper airways. They lodge in tissue that has no effective mechanism for clearing them. Once embedded, they stay. And in the moon's reduced gravity, 1/6 of Earth's particles that would settle quickly in terrestrial air remain suspended far longer, increasing the window of inhalation with every breath. The chemical composition of the dust adds another layer of concern. Lunar regolith is rich in silicates, the same class of minerals that causes silicosis in miners on Earth, a progressive and incurable lung disease. But terrestrial silicosis is caused by particles that have been weathered, rounded, and chemically dulled by exposure to water and atmosphere. Lunar silicate particles have none of that passivation. Their freshly fractured surfaces are chemically reactive. They carry dangling molecular bonds that interact aggressively with biological tissue on contact. Research, published in 2024, took this a step further. Scientists at Stony Brook University subjected lunar dust simulants to artificial space weathering, a process that mimics the bombardment of solar wind particles that the real lunar surface experiences continuously. The treated simulants showed significantly greater toxicity to human lung cells than untreated samples. The solar wind implants hydrogen and helium ions into the outer layers of dust grains, altering their surface chemistry and making them more reactive when they encounter biological material. This means that the dust on the actual lunar surface, which has been bathed in solar wind for billions of years, is likely more toxic than even the sharpest untreated simulant can replicate in a laboratory. And then there is the electrostatic problem. On Earth, humidity in the air helps neutralize static charges on particles. Dust does not cling to surfaces with unusual tenacity because the moisture in the atmosphere bleeds away the charge. The moon has no moisture, Its surface is bombarded by ultraviolet radiation and charged particles from the solar wind, both of which deposit electric charge on regolith grains. The result is dust that is electrostatically sticky to a degree that terrestrial experience does not prepare you for. It adheres to spacesuits, to visors, to tools, to vehicle surfaces, to every material it contacts. Brushing it off does not work. The Apollo astronauts tried. They used brushes, cloths, and compressed gas. The dust came back. It migrated into joints, seals, and connectors. It worked its way into equipment designed to be dust-resistant and defeated the seals designed to keep it out. During the Apollo missions, this was manageable because the exposures were brief. Even the longest mission lasted only days. The astronauts tolerated their clogged sinuses and irritated eyes because they were going home in days. But the missions being planned now are not measured in days. They envision stays of a week or more per mission initially, eventually extending to weeks and months as surface infrastructure develops. The dust mitigation challenge scales with duration in a way that is not linear. A 3-day exposure to lunar dust is an annoyance. A 3-month exposure is a medical risk. A 3-year exposure, the kind that a permanent base would entail, enters territory where the cumulative damage to lungs, eyes, skin, and equipment becomes a defining constraint on the entire operation. NASA established the Lunar Airborne Dust Toxicity Advisory Group, known as LADTAG, specifically to study this problem. Their work has produced recommended exposure limits for airborne lunar dust inside habitats, but the limits themselves reflect a wide band of uncertainty. Early expert workshops produced estimates that spanned a 300-fold range from 0.01 to 3 milligrams per cubic meter for what might constitute a safe, long-term inhalation threshold. That range has narrowed with subsequent research, but the fundamental difficulty remains. There is no long-term human exposure data for actual lunar dust. There never has been. The Apollo exposures were too brief and too poorly instrumented to provide definitive answers. Everything we know about chronic lunar dust toxicity comes from simulants, from animal studies, from cell cultures, and from analogies to terrestrial occupational hazards like coal mining and volcanic ash exposure. Those analogies are useful but imperfect. Lunar dust is not volcanic ash. It is not coal dust. It is something that does not exist anywhere on Earth, and its long-term biological effects on the human body remain, as NASA's own risk documentation states, an open question. Harrison Schmitt himself, now in his 90s, has said plainly that the priority should be to never let astronauts be exposed to lunar dust at all. He described it as primarily an engineering problem. He is right that engineering solutions exist. Airlocks can be designed to minimize dust transfer. Suits can be stored and maintained outside the habitat. Surfaces can be coated with materials that shed particles. Electrostatic cleaning systems can be developed. These technologies are real, and they are being worked on, but every one of them adds mass, complexity, and potential failure modes to a mission architecture that is already operating at the edge of feasibility. And the failure mode for dust mitigation is not catastrophic in the way a hull breach is catastrophic. It is slow. It is cumulative. It is the gradual degradation of seals that let a little more dust through each cycle. It is the imperceptible buildup of particles in an air filtration system that was designed for a lower dust load than it actually encounters. It is the astronaut who develops a persistent cough during week 4 and has no pulmonologist within 250,000 miles. Dust is the threat that does not announce itself with alarms. It simply accumulates, inside the habitat, inside the suit, inside the body, grain by grain, day after day, until the accumulation becomes the problem. And while the dust works its way inward, The temperature works its assault from outside. The Moon's thermal environment is among the most extreme of any solid surface in the inner solar system. At the equator, daytime temperatures reach approximately 127 degrees Celsius, roughly 260 degrees Fahrenheit. That is hot enough to boil water at reduced pressure, hot enough to degrade many polymers, hot enough to create thermal expansion in metal structures that must be accounted for in every joint and seal. Then the sun sets, and the temperature falls. It does not fall slowly, it does not fall gently, it plunges. Nighttime temperatures at the equator drop to approximately minus 173 degrees Celsius, roughly minus 280 degrees Fahrenheit. The total swing from day to night is approximately 300 degrees Celsius, and here is the detail that makes this thermal cycle uniquely punishing. The lunar day is not 24 hours long. It is roughly 29.5 Earth days long. That means the daytime heating lasts for approximately 14 Earth days continuously, followed by 14 Earth days of continuous darkness and cold. Everything on the surface, every habitat, every vehicle, every instrument, every seal on every airlock, experiences 2 full weeks of thermal expansion under direct solar radiation, followed by 2 full weeks of thermal contraction in deep cold. Then the cycle repeats, and repeats, and repeats. The 14-day lunar night deserves to be understood on its own terms, because it is not simply the absence of sunlight. It is the onset of an operational crisis that tests every system a habitat depends on simultaneously. On Earth, night means darkness. On the Moon, night means darkness and the loss of the primary energy source for any solar-powered system, in greens. During the 2-week day, solar panels can generate electricity continuously. The moment the sun dips below the horizon, that power stream drops to zero and does not return for 354 hours. Every watt the habitat needs during that stretch, for heating, for air recycling, for water processing, for lighting, for communication, for keeping electronics above their minimum operating temperatures, must come from stored energy or from a non-solar source like a nuclear generator. Battery storage sufficient to sustain a crude habitat for 14 days at full operational load is an enormous mass penalty. Fuel cells offer better energy density but require consumable reactants. Nuclear systems, specifically radioisotope thermoelectric generators or small fission reactors, are the most promising long-duration option. But they add regulatory complexity, development cost, launch risk, and thermal management challenges of their own. No crude lunar habitat has ever operated through a full lunar night. The engineering is being developed. It has not been demonstrated. And the cold that accompanies the darkness is not passive, it is aggressive. Without solar input, the surface radiates its stored heat into space rapidly, and the temperature drops by tens of degrees within the first hours after sunset. The habitat's thermal control system, which spent the previous 2 weeks rejecting heat to prevent overheating, must reverse its function entirely and begin conserving heat to prevent freezing. The same structure that needed to shed energy now needs to hoard it. The engineering solution to this reversal is not trivial. It requires thermal switches, variable conductance heat pipes, or insulation systems that can change their effective resistance on command. These technologies exist in laboratories and in some spacecraft applications. Deploying them in a surface habitat that must also withstand dust infiltration, radiation degradation, and mechanical wear from repeated thermal cycling is a different order of challenge. The darkness itself affects surface operations in ways that compound every other hazard. During the lunar night, the landscape is invisible. There is no atmospheric scattering to create twilight. There is no ambient glow from distant cities. The terrain beyond the habitat's own lighting drops into absolute black. EVAs during the lunar night, if they are conducted at all, must rely entirely on artificial illumination in a landscape where shadows are total and terrain features can be invisible until an astronaut is standing on top of them. Any maintenance task that requires external repair during the night period is exponentially more difficult and more dangerous than the same task performed in daylight. For the crew inside, the psychological weight of the lunar night is distinct from the stress of daytime operations. 14 continuous days without natural light, without any visual reference to the passage of time beyond the clock on the wall. In an enclosed space where the only view through the window is black and the only sound is machinery. Research on human circadian biology has shown that prolonged absence of natural light disrupts sleep architecture, hormone regulation, and mood stability, even in comfortable terrestrial environments. On the lunar surface, this disruption compounds with the existing stresses of isolation, confinement, and the constant awareness that the habitat's power reserves are being drawn down hour by hour toward a margin that everyone hopes is sufficient, but no one can guarantee. Thermal cycling is one of the most destructive forces in materials science. When a material expands and contracts repeatedly, the interfaces between different materials experience stress. Bolts loosen, adhesives crack, seals deform, solder joints fatigue. The damage from any single cycle may be microscopic, invisible to inspection. But over dozens of cycles, over months and years, the cumulative effect is structural degradation that can compromise systems that were flawless when they were installed. Every engineer who has worked on lunar surface hardware understands this problem. It is not a surprise. It is a known constraint that drives design decisions throughout the entire mission architecture. Materials are selected for low coefficients of thermal expansion. Joints are designed with compliance to absorb differential movement. Redundancy is built into critical seals. Testing protocols subject components to thermal cycling in vacuum chambers before they are approved for flight. But there is a gap between testing and reality that the Moon exploits ruthlessly. Ground-based thermal vacuum testing can simulate the temperature range. It can simulate the vacuum. What it cannot perfectly simulate is the duration, the radiation environment, the dust contamination, and the combined effect of all of these acting on the same hardware simultaneously over months and years of operation. A seal that survives 1,000 thermal cycles in a clean laboratory vacuum chamber may behave differently after 300 cycles on the lunar surface with a thin film of electrostatically bonded dust particles embedded in its contact surface while being irradiated by galactic cosmic rays that slowly degrade the polymer from which it is made. This is not speculation. It is the engineering reality that every long-duration lunar program must confront. The Apollo hardware did not face this challenge because it was never on the surface long enough. The longest Apollo mission experienced only a small fraction of a single thermal cycle. The equipment worked beautifully for 3 days. Whether it would have worked for 3 months is a question Apollo was never designed to answer. The South Pole environment that Artemis is targeting adds its own thermal complications. The permanently shadowed regions where water ice is believed to exist are among the coldest places ever measured in the solar system. NASA's Lunar Reconnaissance Orbiter recorded temperatures as low as -238 degrees Celsius inside some polar craters. At those temperatures, conventional electronics cease to function. Lubricants solidify. Metals that are ductile at room temperature become brittle enough to shatter. Battery chemistry slows to a crawl or stops entirely. Any vehicle or instrument that enters a permanently shadowed region must carry its own heat source powerful enough to keep its critical systems above survival thresholds. And it must do so while operating in an environment where the thermal gradient between sunlit and shadowed areas can exceed 200 degrees across a distance of meters. An astronaut walking near the boundary of a permanently Prebry, shadowed crater would experience something that has no analog on Earth. One side of their suit could be receiving direct solar radiation at full intensity, while the other side faces a void so cold that the thermal load on the suit's environmental control system reverses direction within the span of their intense's own body. The suit must reject heat on one side and retain it on the other simultaneously. The engineering required to manage this is real, and it is advancing. The Axiom suit incorporates thermal management features that the Apollo suits lacked entirely. But the margin between a system working as designed and a system overwhelmed by conditions it was not fully tested against is thinner on the Moon than anywhere else human beings have ever operated. And all of this, the dust, the temperature, the radiation we have already covered, exists within a framework of operational constraints that compound every individual hazard into something greater than the sum of its parts. Consider what an emergency looks like under these conditions. An astronaut is on a surface excursion 4 kilometers from the habitat, investigating a geological feature near the rim of a shadowed crater. Their suit's thermal control system develops a fault. The system that rejects heat from the sun-facing side of the suit begins losing efficiency. The astronaut's core temperature starts to rise. On Earth, the response is simple. You stop, you get to shade, you drink water, you wait for help. On the Moon, there is no shade unless you are near a terrain feature that blocks the sun. There is no ambient air to carry heat away from the suit. The only cooling the astronaut has is what the suit provides, and the suit is malfunctioning. The nearest shelter is 4 kilometers away, across terrain that cannot be traversed quickly in a spacesuit. Running is not possible. The fastest practical movement speed in lunar EVA conditions is a brisk walk. The astronaut must cover 4 kilometers in a degraded suit while their body temperature climbs. The clock on this scenario is not long. Hypothermia becomes dangerous within tens of minutes under sustained heat stress. The astronaut's cognitive function begins to decline before their physical capacity does, which means their ability to make good decisions degrades precisely when they need it most. Their crewmate may be nearby or may be at a separate work site. Communication with mission control involves a time delay of approximately 1.3 seconds each way, small but non-trivial in a fast-developing emergency. And the controllers on Earth cannot physically do anything. They can advise, they can monitor telemetry. They cannot send help. Now layer onto this scenario the possibility that the suit malfunction was caused by dust infiltration into a thermal control valve. The dust that entered the mechanism during the previous EVA cycle, the dust that the cleaning protocol reduced but did not eliminate, the dust that migrated into a crevice that the pre-EVA inspection could not fully examine. The failure was not random. It was the end of a slow process of degradation that began the first time the suit was exposed to the lunar surface, and there was no way to detect it until the system failed. Now consider a different scenario. One that takes place not in the punishing daylight, but in the middle of the lunar night. The crew is inside the habitat on day 9 of the 14-day darkness. The external temperature has stabilized at approximately minus 160 degrees Celsius. The habitat's thermal management system has been operating in heat retention mode for over a week, drawing power from stored reserves to maintain interior temperatures within the livable range. At some point during the night shift, an alert signals that one of the primary heating loops has lost pressure. A micro-leak, Possibly at a joint where a thermal cycling weakened seal finally gave way, possibly at a fitting where microscopic dust particles embedded during a daytime EVA created a pathway that expanded in the cold. The backup loop engages automatically, but the backup was sized for redundancy, not for sustained full-load operation. Its capacity is sufficient for hours, not days. And there are 5 days of darkness remaining before the sun returns. The crew faces a decision. They can attempt an external repair, which means suiting up, exiting into absolute darkness at temperatures that will challenge every material in the suit, navigating to the leak site using only helmet-mounted lights, and performing a repair with gloved hands on a fitting that may be too cold to touch, even through insulated gloves. Or they can attempt an internal workaround, redistributing heat loads, shutting down non-essential systems, reducing the heated volume of the habitat, and hoping that the backup loop holds until sunrise. Neither option is safe. The external repair exposes an astronaut to conditions that no EVA protocol was designed for. The internal workaround means living in a habitat that is slowly losing thermal margin, where the temperature may drop low enough to affect equipment performance, battery efficiency, and eventually human comfort and health. And throughout all of it, Mission Control is watching telemetry with a 2.5-second delay, offering advice that may already be outdated by the time it arrives. This is not an exotic scenario. It is a predictable failure mode. Thermal system leaks are among the most common mechanical failures in pressurized systems operating under thermal stress. The only question is when it happens, not whether it happens. And the severity depends entirely on when in the lunar cycle it occurs. The same leak during the daytime might be an inconvenience. During the night, it becomes a survival problem. This is the nature of risk on the moon. Hazards do not present themselves individually. They layer. Dust degrades seals. Thermal cycling weakens them. Radiation embrittles polymers. The failure that eventually occurs is not the result of one cause. It is the result of an environment that attacks every material, every mechanism, and every biological system from multiple directions simultaneously and never stops. The communication constraint amplifies everything. The roughly 2.5-second round-trip delay between the Moon and Earth is small by interplanetary standards. It is nothing compared to the minutes-long delay for Mars. But it is enough to make real-time guidance during a crisis difficult. A surgeon on Earth cannot talk an astronaut through an emergency medical procedure with the same fluidity they could in a ground-based operating room. A flight controller cannot respond to a rapidly evolving system failure with the same reaction time they could for the International Space Station. The delay introduces a gap between what is happening and what Mission Control knows is happening, and in that gap, decisions must be made by the crew on the surface with whatever training, whatever tools, and whatever judgment they have at that moment. The crew will be small. Current Artemis mission profiles envision 2 astronauts on the surface for landing missions, 2 people. On a world where the nearest reinforcement is 3 days away and the nearest hospital does not exist. If one crew member is incapacitated, the other must manage the emergency alone, while simultaneously maintaining the systems that keep both of them alive. End quote. Unquote. End quote. There is no second shift. There is no option to step outside for a moment and collect yourself, because outside is the most hostile environment within 250,000 miles. The psychological dimension of this has been studied extensively in analog environments on Earth, in Antarctic research stations, in submarine deployments, in isolated confinement experiments. The findings are consistent. Small crews in isolated, confined, and extreme environments experience predictable patterns of stress, interpersonal friction, sleep disruption, cognitive fatigue, and motivational decline. These effects begin to manifest within weeks and intensify over months. The countermeasures are well known: careful crew selection, structured schedules, communication with support networks, access to private space, and the knowledge that the duration of isolation is finite and the return home is certain. On the Moon, some of these countermeasures apply. Others do not. The crew will be carefully selected. Schedules will be structured. Communication with Earth will be maintained. But the psychological awareness that you are standing on a surface that will kill you if any one of a dozen systems fails, that the nearest human being who is not your crewmate is farther away than any explorer in history has ever been from help, that a solar storm could force you into a cramped shelter for days with no certainty about when it will end, these stressors do not have clean countermeasures. They are woven into the fabric of the experience. They are the experience. The analog research is informative, but inherently limited. Antarctic winter-over crews at stations like Concordia, which is sometimes called White Mars for its isolation and extreme conditions, experience a well-documented syndrome of cognitive slowing, emotional flattening, and interpersonal withdrawal that researchers call the winter-over syndrome. Thyroid hormone levels shift, sleep quality degrades. Task performance on cognitive tests measurably declines by the third month, and Concordia, for all its severity, has breathable air outside. It has a solid planet beneath it that will not kill you if a wall cracks. The crew knows, at a level so deep it does not require conscious thought, that the environment outside is hostile but not instantly fatal. A person caught outside in an Antarctic storm has minutes to find shelter. A person caught outside on the lunar surface without a functioning suit has seconds. That distinction changes the psychological calculus in ways that no analog can fully replicate. The awareness of immediate lethality, the knowledge that the only thing between you and death is an engineered system that must function continuously without interruption, produces a form of chronic vigilance that does not resolve with rest. It sits underneath every task, every meal, every conversation. Submarine crews report a version of this, the constant background awareness that the hull is the only barrier between life and the crushing pressure of deep water. But submarines operate with crews of dozens or hundreds, with a command hierarchy, with medical officers, with redundant watch-standing schedules that allow any individual to step away from responsibility for a defined period. A two-person lunar crew has none of that diffusion. The weight of vigilance is concentrated on two people who must also be each other's physician, mechanic, counselor, and sole companion for the duration of the mission. There is a body of research on what psychologists call the third quarter phenomenon, a pattern observed in isolated expeditions where morale and performance reach their lowest point roughly 3/4 of the way through the planned duration. At that stage, the initial excitement of the mission has faded, the novelty of the environment has worn off, and the remaining time feels longer than the time already served. On the Moon, the third quarter phenomenon would arrive in the context of an environment that is already applying every other stressor described in this story: dust in the airways, radiation in the cells, equipment that is incrementally more worn than it was at the start, sleep that has been fractured by the unnatural rhythm of the lunar day-night cycle, and the grinding knowledge that the return home is still weeks away. The Apollo astronauts managed these pressures for days. They were test pilots, selected precisely for their ability to function under extreme stress for short periods. The missions were designed to be brief enough that psychological degradation was not a primary concern. Sustaining that performance for weeks or months under conditions that are objectively more dangerous than anything Apollo faced is a categorically different challenge. And it is a challenge that cannot be fully tested in advance. No analog environment on Earth replicates the lunar surface. Antarctica is isolated, but it has air. Submarines are confined, but they are surrounded by water that can be used for cooling and shielding. The International Space Station is in space, but it is in low Earth orbit, within the magnetosphere, 90 minutes from any point on Earth by re-entry trajectory. No facility on this planet can simultaneously replicate the vacuum, the radiation, the dust, the thermal cycling, the gravity, the communication delay, and the absolute absence of rescue that define the lunar surface. The astronauts who go will be the test subjects. Their missions will be the experiment. And the results will be written not in publications but in the health of their bodies, the integrity of their equipment, and the decisions they make when something goes wrong at 3 in the morning of a 14-day night. The moon does not need to produce a single spectacular disaster to prove how severe it is. It only needs to apply its ordinary conditions to human beings and their machines for long enough. The dust that clogs a valve, the thermal cycle that cracks a seal, the radiation that damages a circuit board, the cold that drains a battery faster than the power budget predicted, the cumulative fatigue that causes an astronaut to misread a checklist. None of these is dramatic. None of them makes for a compelling movie scene. But any one of them, in the right combination at the right moment, is enough to turn a manageable situation into an unrecoverable one. This is the moon that awaits the next generation of explorers. Not the moon of flags and footprints and triumphant speeches, but the moon of slow attrition, compounding hazards, and margins that tighten with every passing day. It is a world where the environment never rests, and the humans inside it cannot afford to rest either. And the deepest irony of all is that this world, this relentless, grinding machine of dust and radiation and cold, is the one that humanity looks up at every night and calls familiar. The rest of this story is about that irony, and about what it means for the future of everything we are trying to build beyond this planet. There is an instinct buried deep in the human brain that has saved countless lives over hundreds of thousands of years. It is the instinct that says close means reachable. If you can see something, you can get to it. If you can get to it, you can get back. The campfire across the valley, the shoreline from the water, the village from the hilltop. For nearly all of human existence, this instinct was correct. The things you could see were the things you could survive reaching. Distance was danger, closeness was safety. The equation was simple, and it worked. The moon breaks that equation. It breaks it so completely and so quietly that most people do not realize it has been broken at all, because the moon is right there. You can see it from your yard. You can watch it cross the sky. You can photograph its craters with a consumer telescope. Children point at it before they can speak in full sentences. It is the most visible, most present, most familiar object in the night sky. And every fiber of the ancient brain registers that familiarity and translates it into a single unconscious conclusion. It cannot be that dangerous. It is too close to be that dangerous. This is the illusion that makes the moon more psychologically treacherous than almost any other destination in space. Not because the danger is hidden. Everything described so far in this story is published, documented, and available to anyone who looks for it. The radiation data is public. The dust research is in peer-reviewed journals. The thermal measurements are hosted on NASA's own servers. None of this is classified. None of it is secret. The danger is not hidden. It is ignored. And it is ignored because the brain has already made up its mind. The moon is close, therefore the moon is manageable. End of analysis. Mars does not suffer from this problem. Mars sits at a minimum distance of roughly 54 million kilometers from Earth when the two planets are at their closest orbital approach, and the average distance is considerably greater. A one-way communication signal takes between 4 and 24 minutes depending on orbital positions. A crewed mission to Mars would take approximately 7 months each way using current propulsion technology. Nobody hears those numbers and feels comfortable. Nobody looks at Mars and thinks, we have handled this before. Mars earns its reputation as hostile simply by being far away. The distance alone activates the brain's caution circuits. People instinctively understand that Mars is a commitment, an ordeal, a journey from which return is not guaranteed on any human timescale that feels natural. The Moon is 3 days away. 3 days. The Apollo astronauts proved it. The Artemis II crew just confirmed it. 3 days from launch to lunar orbit. The number sits in the public mind like a safety blanket. If something goes wrong, we can come home in 3 days. The Moon is not like Mars. The Moon is close. We have a way back. But 3 days is not what rescue looks like. 3 days is the transit time for a spacecraft that is already fueled, already in the correct orbital position, already loaded, and already launched on the optimal trajectory. It describes the journey from the Moon to Earth under ideal conditions. It does not describe the time required to respond to an emergency on the lunar surface, because an emergency does not wait for ideal conditions. Consider what actually happens when something goes wrong. An astronaut on the surface reports a medical emergency. The crew assesses the situation and determines that evacuation to Earth is necessary. Before the ascent vehicle can launch from the surface, it must be prepared. Systems must be checked. The vehicle must be in a configuration suitable for departure. The crew must be aboard and secured. If the emergency has damaged surface infrastructure, or if the crew member who is injured is the one with specialized knowledge of the ascent vehicle systems, the preparation time extends. Once the vehicle leaves the surface, it must reach lunar orbit. Once in lunar orbit, it must perform a trans-Earth injection burn at the correct time and in the correct orientation. Then begins the 3-day coast back to Earth. Then comes re-entry, descent, and splashdown or landing. Then comes recovery by naval or ground assets that must be pre-positioned. Then comes transport to a medical facility. The total elapsed time from the moment of the emergency to the moment the astronaut is in a hospital is not 3 days. It is likely 5 to 7 days under favorable conditions. Under unfavorable conditions, with complications in any of those steps, it could be longer, and for certain types of emergencies, the types that kill within hours, no evacuation timeline is fast enough. A stroke, a severe anaphylactic reaction, a penetrating injury from a micrometeorite fragment, a suit breach in a remote location, these events do not grant 5 days of grace, they grant minutes. And there is no emergency room on the Moon. There is no surgical theater. There is no blood bank. There is no pharmacy stocked with more than a limited mission medical kit. There is whatever the crew brought with them and whatever they know how to do. The International Space Station, which is often invoked as a model for how humans can live in space, operates under a fundamentally different risk calculus. The station orbits at 400 kilometers above the Earth's surface. A Soyuz capsule can undock and return a crew member to Earth within a few hours. The station is in continuous contact with mission control except for very brief communication blackouts. It sits within the magnetosphere. It has been continuously inhabited for over 25 years, and during that time, a robust infrastructure of resupply, crew rotation, and emergency protocols has been developed and refined. If a critical system fails on the station, a replacement can be launched within days to weeks. If a crew member develops a medical condition that requires evacuation, the option exists and has been used. None of that infrastructure exists for the Moon. The logistics chain for lunar surface operations is still being developed. There is no permanent orbital asset around the Moon waiting to facilitate rapid evacuation. The Gateway Station, which is planned to support later Artemis missions, is not yet deployed and will not provide the same level of continuous support that the ISS receives from Earth. Resupply missions to the lunar surface will be infrequent and expensive. Each kilogram of material landed on the Moon costs orders of magnitude more than a kilogram delivered to low Earth orbit. The margin for error is thinner, the consequences of failure are more severe, and the options for recovery are fewer. This is what closeness actually means in the context of the Moon. It means that the destination is near enough to create the expectation of safety without being near enough to deliver it. The 3-day transit time is close enough to sound manageable, but long enough to be fatal in a time-critical emergency. The communication delay is short enough to allow real-time conversation, but long enough to prevent the kind of instantaneous ground-based intervention that crews on the ISS rely on. The Moon sits in a zone that is uniquely dangerous because it is uniquely deceptive, far enough to be deadly, close enough to be underestimated. There is a concept in aviation safety that maps directly onto this kind of hazard. Pilots and safety engineers describe what happens when an aircraft appears to be performing normally but is actually approaching a condition from which recovery is not possible. The crew feels no danger. The instruments may not show it. Everything looks and feels fine right up until the moment it is not. The Moon is this concept made planetary. It looks fine. It feels close. The numbers seem manageable. And underneath that appearance, the environment is assembling a set of conditions that do not forgive. There is another dimension to this illusion that operates at the institutional level rather than the individual one. Because the Moon is perceived as close, the political and budgetary structures that support lunar exploration tend to treat it as a nearer-term, lower-risk endeavor than deep space missions. This perception influences design decisions, timeline expectations, risk tolerance thresholds, and the allocation of resources for contingency planning. When a destination is perceived as close, the pressure to move quickly increases. The tolerance for delays decreases. The willingness to invest in redundancy and backup systems, which are expensive and slow to develop, competes against the desire to meet schedules and demonstrate progress. The Artemis program has experienced this tension visibly over the past several years. Timelines have shifted repeatedly. The first crewed landing, originally targeted for 2024, has been pushed to 2028. The heat shield on the Orion capsule experienced greater erosion during the Artemis I uncrewed test than models predicted, prompting additional investigation and contributing to schedule adjustments. The development of the human landing system, being built by SpaceX and Blue Origin under commercial contracts, has encountered delays. Some Starship flight tests experienced anomalies resulting in the loss of the vehicle. These are not failures in the catastrophic sense. They are the normal, expected challenges of developing complex systems for an extraordinarily demanding environment, but they illustrate a pattern. The Moon is harder than the timeline assumes. The environment demands more of the hardware than early models predicted. And each delay, each redesign, each additional test cycle represents the slow collision between institutional optimism and physical reality. None of this means the program is doomed. The engineering talent working on Artemis is world-class. The science objectives are compelling. The strategic logic of establishing a presence on the Moon as a stepping stone for deeper space exploration is sound. What it means is that the difficulty of the enterprise is systematically underappreciated by the public conversation surrounding it. The celebratory framing, the emphasis on milestones and firsts, the countdown to landing dates, all of it creates an impression of momentum that is real, but that can also obscure the enormity of what remains unsolved, because what remains unsolved is not a single engineering problem. It is the integration of dozens of engineering problems, each of which interacts with the others in ways that cannot be fully predicted until hardware meets the actual lunar environment. Dust mitigation interacts with thermal management. Thermal management interacts with power systems. Power systems interact with communication reliability. Communication interacts with medical response capability. Radiation protection interacts with habitat mass, which interacts with launch vehicle capacity, which interacts with cost, which interacts with political will, which interacts with timeline pressure, which circles back to the question of how much redundancy and margin the program can afford. This web of interdependencies is what makes the Moon so much harder than it appears. Any single problem on the list can be solved in isolation. The challenge is solving all of them simultaneously in a system that must function without interruption on a surface where every hazard compounds every other hazard, and no single margin can be evaluated in isolation. The Apollo program solved this for 3-day missions. It did so brilliantly. But the solution space for a 3-day mission and the solution space for a 3-month mission are not related by a simple scaling factor. They are qualitatively different problems. The way building a campfire and building a power plant are different problems. Both involve combustion. The similarity ends there. The implications of all this reach beyond engineering into something more fundamental about how humanity relates to the spaces it seeks to occupy. Every environment that human beings have colonized on Earth, from tropical forests to Arctic tundra to deep ocean floors, has required a period of learning that was measured not in missions but in generations. The first people to move into a new biome did not arrive with a complete understanding of its hazards. They learned through experience, through failure, through loss. The accumulated knowledge of how to survive in a particular environment was built slowly, tested against reality, and passed forward. The process was long and often brutal. The Moon does not allow that process. There is no margin for generational learning through trial and error on a world where a single error can end a mission and potentially end lives. The knowledge must be front-loaded. The understanding of the environment must be as complete as possible before human beings commit to staying. And the current state of that understanding, while vastly greater than it was during Apollo, is still incomplete in ways that matter. We do not have long-term human exposure data for lunar dust. We do not have long-term data on the combined effects of radiation and dust on human physiology. We do not have operational experience with habitats that must survive years of thermal cycling on the lunar surface. We do not have a validated medical protocol for emergency surgery in 1/6 gravity in a dust-contaminated environment with a communication delay to the nearest physician. We do not have a proven method for extracting and processing lunar water ice at a scale sufficient to support sustained human presence. Each of these gaps represents a question that will be answered by the missions themselves, which means the astronauts who go will be the ones providing the answers in real time, with their own bodies and their own judgment, on a surface that does not offer second chances. The surgical question alone is staggering in its implications. On Earth, emergency abdominal surgery requires a sterile operating theater, a trained surgical team of at least 3 to 4 people, anesthesia equipment, a blood supply, and post-operative monitoring that lasts days to weeks. On the lunar surface, you have a 2-person crew, a medical kit that must be small enough to fit within a mass-constrained habitat, no operating theater, no anesthesiologist, no blood bank, and a recovery environment where the patient must return to operational duty as quickly as possible because there is no one to replace them. Researchers have conducted simulated surgeries in microgravity aboard parabolic aircraft flights, and the results have demonstrated fundamental problems with fluid management, instrument stability, and the behavior of exposed tissue when gravity is reduced or absent. At 1/6 gravity on the lunar surface, blood would still settle downward, but more slowly and with less predictable spread. Fluids would migrate along surfaces differently than surgeons are trained to expect. The simple act of holding tissue in place for suturing becomes harder when instruments and hands behave with unfamiliar lightness, and when the patient's body responds to manipulation with different resistance than it would on Earth. These are not theoretical objections. They are extrapolations from controlled experiments conducted in conditions that are themselves only approximations of what the Moon would impose. The habitat survivability question is equally open. No structure designed for the lunar surface has been tested under actual conditions for more than a few hours. The longest operational hardware on the Moon has been robotic, and even those systems have experienced failures driven by the thermal and dust environment. The Soviet Lunar rovers, the longest operating surface vehicles of the 20th century, survived for months but eventually succumbed to thermal issues. The Chinese U-2 rover experienced a mechanical failure linked to the harshness of the lunar night during its first operational cycle. These were machines with no life support requirements. A crewed habitat must do everything these machines did and simultaneously keep human beings breathing, warm, hydrated, fed, and psychologically functional. The engineering confidence that such a system will work as intended for months rests on analysis and testing. It does not rest on demonstrated performance, because that demonstration has not happened yet. This is not an argument against going. It is an argument against going casually. It is an argument against allowing the familiarity of the Moon, its closeness, its visibility, its place in cultural memory, to substitute for a clear-eyed understanding of what it actually takes to survive there. The Moon deserves the same respect that any hostile environment deserves, not less respect because we visited it briefly half a century ago, but more, because that brief visit taught us just enough to know how much we do not know. The Apollo astronauts understood this. They were test pilots. They knew they were flying into danger. They prepared for it with the intensity that danger demands. They accepted the risk with open eyes, and they were going for days, not months. The astronauts who follow them to the surface under Artemis will need to maintain that same intensity, not for a sprint, but for an endurance race, in conditions that are objectively more demanding than anything Apollo faced, with mission objectives that require sustained performance rather than peak bursts. The romantic image of the Moon, the silver disk in the sky, the symbol of aspiration, the place where humanity first set foot on another world, that image is beautiful. It is meaningful. It represents something genuine about the human spirit. But it is not the Moon. It is a story about the Moon, and stories, no matter how beautiful, are not survival plans. The Moon that waits for the next generation of explorers is not a symbol, it is a place. It is a specific, physical, measurable environment with specific, physical, measurable properties. Its surface is coated in toxic glass. Its sky offers no protection against the most energetic particles in the universe. Its temperature swings across hundreds of degrees on a cycle measured in weeks. Its gravity is low enough to keep poison dust suspended in the air of any enclosed space. Its distance from Earth is short enough to suggest rescue and long enough to prevent it. And it has been sitting there in exactly this configuration for 4.5 billion years. It was this hostile before Apollo, it was this hostile during Apollo, and it will be this hostile when the next boots touch down. The harsh truth about going back to the Moon is not that we should never do it. The science is worth pursuing. The engineering challenges are worth solving. The strategic vision of extending human presence beyond Earth is worth the effort and the risk. The harsh truth is that the Moon is not what most people think it is. It is not a familiar destination made safe by proximity and precedent. It is one of the most punishing environments any human being has ever been asked to enter, made more dangerous by the fact that it does not look punishing. It looks gentle. It looks close. It looks like it is waiting for us. It is not waiting. It does not wait. It does not care. It is 250,000 miles of vacuum and regolith and radiation that will test every system, every plan, every assumption, and every human body that touches its surface. The astronauts who go will face this test, knowing what they are walking into, because that is what astronauts do. They accept the risk. They do the work. They represent the best of what our species is capable of. But the rest of us, the ones who watch from Earth, the ones who celebrate the launches and cheer the landings and count down to the next mission, we owe them something in return. We owe them the honesty of understanding what they are facing, not the storybook version, not the inspirational edit, not the version that fits in a headline or a social media post, the real version. The version where the moon is beautiful and brutal, close and unreachable, symbolic and indifferent, all at the same time. The most unsettling truth about the moon is not that it is dangerous. Danger can be assessed, planned for, mitigated. The most unsettling truth is that it is the easiest destination in all of space to underestimate. It is the world that humanity knows best and understands least. It is the place that looks like home from a distance and behaves like hostility up close. And the gap between those two realities, the gap between how the moon looks and how the moon is, may be the single greatest risk factor in the entire future of human exploration beyond Earth. The next time you look up at the moon on a clear night, notice how calm it looks, how still, how familiar. It has looked exactly like that for every human being who has ever lived. It looked like that for the Apollo crews before they left, and it looked like that when they came back. It will look like that for the Artemis crews when they go, and it will look like that when they return. Nothing about its appearance will change, but if you have listened to everything in this story, something about the way you see it might. That silver light is reflecting off a surface coated in shards of glass finer than flour. That dark terrain is baking at hundreds of degrees or freezing at hundreds below. That quiet grey face is being hammered by particles that would shred your DNA if you stood on it unprotected. And that gentle nearness, that 3-day distance that feels so manageable, is a lie the ancient brain tells because it cannot accept that something so close could be so severe. The moon is the most beautiful deception in the night sky. And the astronauts who go there next will walk into it with their eyes open, carrying everything they need on their backs, knowing that the ground beneath their boots is not welcoming them, it is tolerating them. For now, for as long as their engineering holds, for as long as their bodies endure, for as long as their luck and their skill and their preparation can keep the silence from swallowing them whole. That is the harsh truth about going back to the moon. Not that we should never go, but that we should never go believing it will be easy. Because the moon has never been easy. It has only ever been close. And close, in space, is the most dangerous thing a destination can be.